Hey everyone, we're live. We're getting everything tweeted out right now. I am your host, Scott Lewis, and we're going to be doing something a little bit different this time. We're going to be trying to export these and produce them as a podcast as well. So, in probably like 3 minutes, I'm going to start the show and be all, you know, professional or something. But if you want to ask us questions during the show, we'll try to answer them at the end of it. Or, since this is a multi-part series, we will try to also address them afterwards in the following episodes. So feel free to tweet at me, Scientific Scott, also Katie Mack at Astro Katie, and leave us a question right there. Or it's focused on you. So also leave us comments on YouTube. So in this video, you can leave them below. Also on Google Plus in the event page where the Q&A app is in. I have the Q&A app loaded. Lots of different ways for you to ask questions about dark matter. Like I said, we're going to be doing a bunch of videos on this to try to dig a little bit deeper than rushing through. So this way, if there are a lot of questions on a single topic, we can dedicate an entire show to that and try to go there.
Because dark matter is way too cool for just one show.
For sure, absolutely. Yeah. And it's totally simple. I mean, we're just milking it for what it's worth. Dark matter is so easy to understand. All right. Well, I am going to get this show going, and let me close all the other one of my tabs so I can actually focus on hosting the show because I see all the tweets. Hi, Twitter. All right, let's do this.
Okay.
Hello, everyone. I am Scott Lewis, your host from Space Fan News, and welcome to another conversation with an astrophysicist. With me, as always, the wonderful Katie Mack. How are you doing today, Katie?
Hello. I'm all right. How are you?
I'm a little tired. It's late, but it's in the afternoon. But we're in the same day right now. So
that's true.
That's awesome.
Are we? Is it not after? Oh yeah, it's after midnight. Yeah.
It's after midnight. So
welcome to Saturday.
Day. Yes. Happy Saturday, everybody. How's the future? Has anything died yet?
It's great. The future is awesome. We've all got jetpacks, so just waiting for you to get there.
Awesome. Send them to me. Well, what we're going to be doing for not only this episode, but in the next following episodes, we are going to be digging into dark matter. We let everyone know as we're recording this live as well and broadcasting it live that people can interact with us. I am Scientific Scott on Twitter, and Katie is at Astro Katie. And we will try to dig in a little bit deeper, but this first episode we're going to be doing just a general overview about what dark matter is, how it was discovered, and get a good primer for when we dig deeper in the following episodes. So, Katie, what is dark matter?
Okay. So dark matter it's a kind of matter, and when we say matter, we mean something that has mass. That's basically all you need to know about matter. It has mass. So it interacts with gravity, and it has a gravitational force, or gravitational attraction, so things are attracted to it. It's attracted to other things through gravity. So it's kind of matter, but it's invisible. So I think some have suggested that dark matter is not a great name for it because it's not dark in the sense of like, a black thing is dark. It's dark in the sense of you can't see it. And I'll talk a little bit more about why you can't see it, but it is invisible, and it is matter, and it just so happens that it's most of the matter in the universe. It's about 85% of the matter in the universe.
Is that just our luck?
It's completely invisible.
Most of the matter in the universe, we can't even see it. That's amazing.
Yeah, and that's not even talking about dark energy, which is most of the energy density in the universe, and that like totally dwarfs the amount of stuff that dark matter is even. But just sticking to matter for the moment, we can talk about dark energy in some other episode.
I'm sure we will.
Yes. So it's most of the matter in the universe, and if you were able to if you're able to see all the matter in like a galaxy, and you can't because most of it's dark, but if you're able to see that dark matter, it would be most of the stuff of a galaxy, and like you have this huge like galactic halo. It's called like a sort of like ball of matter, and then inside is a little tiny galaxy just in sort of the center part.
Right.
So it's so it's like it's most of the stuff of a galaxy, and it's most of the stuff that makes up like the cosmic web. So the like I don't know,
my favorite images of that. It's just so mind-boggling, amazing seeing the cosmic web, the filamental structure of the grand scale. Oh, love it.
Yeah, so like the universe is made of like clusters and filaments of matter, and it makes this sort of web-like structure where there's voids and there's like sort of web things connecting everything, and most of that is made of dark matter. Also.
So how do we know that it's made of dark matter? I mean, we can see the halo, we can see the galactic bulge, but so okay, we can see that, and we just went over that we can't see dark matter. So how do we know that that's there?
So we know that dark matter is So we know that dark matter is there because we can see how it makes other things move around. We can see how it affects the motion of other things that have mass that we can see, like stars and galaxies and gas and things like that. And we also see that it affects the way that light moves because of gravitational lensing. So gravitational lensing is where matter of some kind warps the shape of space-time and makes light move in a different way, and I'll talk about that a little bit more slightly later on. But
we know I've got some pretty images, and if you're listening to this on the podcast, I will put it into the show notes as well.
Okay. So we know about it through basically the way that it makes things that we can see move. So it's like you know those like sort of light paintings where people move flashlights around and then take a long exposure picture, and you see like, you know, some kind of shape that they've made by like spinning a flashlight around or spinning some kind of light around. You can't see whatever's doing the spinning, but you know that something did it because all that light was moving around in a way that you just would not expect otherwise.
Right.
And so it's similar with dark matter, where we look at the way that stars and gas and galaxies move, and the way they're moving just does not make sense with the stuff that we see that's already there. So there are two people who were like really important in the discovery of dark matter as like a part of the universe. Mm-hmm. The first one in chronology was this guy called Fritz Zwicky, who was around in the 30s, and he was looking at how it's a good name. He was quite a character as well. You should look him up, Fritz Zwicky. So he looked at the way that galaxies moved in a cluster of galaxies. So there's this cluster of galaxies called the Coma cluster. It's got lots of galaxies in it, and those galaxies move around like they sort of orbit the center of the Coma cluster, like bees, you know, sort of moving around. And he looked at the way that they moved around, and they all move around because they're sort of orbiting the center of mass of this cluster, right? So they're all kind of orbiting around sort of each other. They're in this sort of gravitational bond. And he looked at how they moved, and they were moving too fast. And he counted up all of the clusters, all of the galaxies in the cluster, added up how much mass that would be, and like it was just everything was moving too quickly. And the only way to explain that was that there's some kind of gravity, some kind of extra stuff with gravity, some kind of extra gravity holding all these little clusters, all these little galaxies into the cluster, and otherwise they would have flown away, and because they were just going too fast. And so he proposed that in the 1930s, and everybody was like, nah, that's a silly idea. And
silly Zwicky in your science.
Yeah, so it wasn't, not everybody said that, but it wasn't like accepted at all for a long time. It was kind of assumed that, you know, the measurements were wrong, or, you know, that he had the wrong idea about something. And then in the 1970s, another astronomer called Vera Rubin came along, and she did a detailed study of how stars move around in disk galaxies, so spiral galaxies. So our galaxy is a spiral galaxy, so it's kind of in a flat disk, and there's stars and stuff in the disk, and the stars move around the center over the course of like millions of years. And they go around, and you can measure in other galaxies and to some extent in our own how quickly all these stars are moving around. And if you had, so if you look at a spiral galaxy and you add up all of the matter that you can see in that spiral galaxy, you see like a bulge in the center, and you see a bunch of stars, and you see some gas. You can count up how much matter that is and how much gravity it should give you, and then you can calculate based on that how quickly the stars should be moving around, because based on sort of any kind of gravitational theory, the speed at which things move around when they're gravitationally bound and orbiting something is just based on how much matter is in the center, and to some very small extent how massive the thing moving around is.
Right. And how far away it is, right?
Yeah, how far away it is and how quickly it's moving. So like in our solar system, most of the matter is in the center, in the sun. Mm-hmm. And so as you move out in the solar system, the things orbiting very close, like Mercury and Venus, are moving very quickly. And as you go farther out, for more distant objects like Jupiter and Neptune are moving much more slowly. And they take a really long time to go around because they're very far out and they're moving a lot more slowly. And so this is, so you can make a graph of that, and basically the speed of the things that are close in are moving very fast, or the speed of those things is very high, and the speed of things far away is very low. And so there's this kind of curve that you get, and that's called the rotation curve. And so Vera Rubin worked that out for a bunch of different galaxies, and for galaxies it should be about the same as for solar systems, in that most of the gravity, most of the massive stuff is in the center. And
right, because we're seeing that bulge and that halo and the supermassive black hole. We're expecting it all in the center, right?
Yeah, I mean the halo. So when we talk about the halo of galaxy, we're usually talking about like the stuff that's orbiting a little bit farther away, and then we're talking about the dark matter halo. But the bulge in the center is like the thing with most of the mass, and then there's the disk, and the disk doesn't have very much mass at all. It's pretty thin. And so stars that are very far away toward the outside of the disk should really be orbiting as though almost all the mass is in the center. And you can figure out how much mass that is. And so as you go out farther out in the galaxy, it should just drop off. Just like in the solar system, you should have things farther out moving much more slowly. So so this picture that you've just put up is a rotation curve. And what Vera Rubin found was that instead of the velocity, the rotational speed going down as you go far out toward the edge of the galaxy, that's the calculated curve, the red curve there, what she saw is that the rotation speed really didn't go down. So it kind of just kept going out straight. She got all these flat rotation curves. And that's really strange because so based on how much matter you can how much matter you can see in the galaxy, those stars toward the edge that are moving really fast ought to just fly off the galaxy.
Right. That's like saying that Neptune has the same orbital period as Mars. I mean, that's kind of silly,
no, it's not
right?
the same. It's not the same orbital period, but it's the same orbital speed. So Neptune would still take longer to get around, but it would be going just as fast, which it can't do, right? Like if it would fly off into space. So it's like if you have one of those kids swing things where they have at carnivals where you're on swings and it goes around and everybody kind of flies off toward the edges.
Right.
But, you don't actually fly off the swings. It would be like those things would fly. Everybody would fly off. People would be scattered everywhere.
See you later, solar system. I'm out of here.
Yeah. So do you have the picture of Vera Rubin's data from the spiral galaxies? Because that's a really cool picture.
It is a really cool picture.
So she looked at a whole bunch of spiral galaxies, and she actually wasn't looking at the way the stars move. She was looking at the gas toward the edges of the galaxies moving. But that's even cooler because you can see when you do that the gas toward the edge of the galaxy is still moving just as fast, even when you can't see any more stars. So like even beyond where the stars end, like you still have everything moving really fast. So like something is holding even the stuff at the very, very edges into this galaxy moving so fast. So this picture shows you the distance from the nucleus, which is the distance from the center of the galaxy, in kiloparsecs, which is thousands of parsecs, and parsecs are like 3 light years or something.
Yeah, a little over 3 light years.
And then, yeah, a little more than 3 light years. And then the rotational velocity, so how quickly everything's moving in kilometers per second. And what you see is for all of these galaxies that she looked at, all of these rotation curves basically flatten out. As far as you can see, whatever you're measuring, in this case she's measuring the gas, as far as you can see the gas, it's moving at about the same speed, 25,000 kiloparsecs away as it is 5,000 kiloparsecs away from the center. So, or 5,000 parsecs away. So like, you just have this huge range where everything's going just as fast. And so the only way that can happen is if there's more matter holding everything in than what you can see. And so what was discovered was that means.
Well, hold on just a second. So,
yeah.
So we're saying there, the reason why we know things are going on in our solar system is that the center of mass is our sun. That's where the main amount of mass is, and then we have a center of mass between our objects, and it happens just to be also inside the sun. So we're orbiting that. Now they're saying that this center of mass is actually distributed more, that it's more like a merry-go-round type thing, where the center of the merry-go-round is also more towards the outside, or
it's more that, so it's not that exactly. It's more that like the stuff that's, so if all of the matter is concentrated at the center, like within the orbit of a thing, so like in our solar system, almost all the matter is concentrated within the orbit of Mercury. So if you were to calculate the orbital speed of something orbiting at the distance of Mercury of the same thing, the same sort of concentration of matter, and you were to calculate the speed of something orbiting at the distance of Jupiter, and all the matter is still just where Mercury, just within the orbit of Mercury, then you'd get this nice rotation curve where everything falls off. In the galaxy, it turns out, in spiral galaxies or in any galaxies, you can't make that approximation because there is more matter. Like, because the amount of dark matter, it goes down somewhat as you go farther out, but it's not all concentrated at the center. It's not all in a single point. So there's still a lot of dark matter within, like, as you go farther out. So you can't make that approximation that everything's at the center because you're actually embedded in this dark matter, like, sphere, kind of, So, like, you have this huge concentration of dark matter that just keeps going as you go out. And so there is more matter holding a more distant star in than there is holding a close-in star. So the close-in star only cares about the stuff within its radius, and there's less of it than there is for the thing that's farther away. So even though that thing is farther away, it's seeing a much stronger pull because it's seeing a sort of the same kind of pull because there's more matter.
Right.
And so the gravitational pull kind of doesn't really change, which means the velocity doesn't really change. So you see what I mean?
So think about it. At that time, Zwicky's seeing these, and now we're seeing this as well. I'm like, that's got to blow their mind. There is something that's making it. I mean, just even thinking about that right there, it's like, you're having something pull in the same amount as something that's very close, close to the center.
Yeah.
What? That would cause all these questions, which it did. I mean, that's our big source of, okay, there's something else going on here.
Yeah.
Which kind of gives it its name, which a lot of people don't like its name, because we can't see it.
Well, yeah. So I mean, they called it dark matter because it was dark in the sense they couldn't see it, but it's not. We know now, and we pretty much knew then, that it's not dark in the sense of, like when something is dark, like when something is black, like this thing is black. It's black because it's absorbing light, not reflecting it. Dark matter doesn't absorb light. So this
doesn't
brings
interact
us to, like,
with the spectrum at all.
Yeah. So this brings us to, like, some of the major properties of dark matter. For most matter, for everything that we can see and touch, if you put your hand on the table, your hand does not go through the table, and the reason it doesn't go through the table is because there's electromagnetic repulsion between the table and your fingers, and that's what keeps us from passing through things, is that electromagnetic repulsion from the.
Which is good because I'm on the 3rd floor in my LA apartment. I would like to stay here.
Yeah. But with dark matter doesn't feel electromagnetic anything, right? So it doesn't feel that repulsion, and it doesn't interact with light. So light, when we see something, it's because light is bouncing off of it and hitting us. And so we see that reflection. We see things through the reflection of light or the production of light. Dark matter doesn't produce light and doesn't reflect light, so we cannot see it. So light passes right through it, and everything else passes right through it, right? So like, although it has gravitational attraction, it doesn't have any kind of collisional stuff that we know about. So, or at least in any way that we've been able to measure, it doesn't produce light, it doesn't absorb light, it doesn't collide with things, it doesn't collide with itself. So dark matter just passes through everything, everything passes through dark matter, but it still has gravity.
So, and this brings me to, I guess, our next point on, okay, so it's not emitting, absorbing, it's not interacting with light at all.
Yeah.
But it still changes what we see when when we're observing objects behind things that have lots of dark matter.
Yeah.
What's going on with that? Because you're saying here, oh, it doesn't interact, but I'm seeing it doing something to this light. What's happening?
Yeah. So what it's actually doing is it's messing with space-time.
What?
So everything that has gravity messes with space-time. So there's this connection between space-time and gravity and like mass, right? So what Einstein figured out, which was like his big insight in general relativity, was that so the way they phrase it is mass teaches space how to bend, and space teaches mass how to move, or something like that. Tells mass. So whenever something has mass, it puts like a dent in space-time. And you can't really, it's not, I mean, this is an analogy. So like there's this analogy where you have like a trampoline, and you put a bowling ball in the center of the trampoline, it makes a dent. And this is like an analogy for how mass bends space-time. Space-time being like the fabric of the universe, basically.
And I think the only problem with that analogy is that we're talking about a plane, so that's 2 dimensions, but now we're worrying about
like
3-dimension denting, which is hard for us to visualize.
It's hard, yeah. But basically, if you have a massive object, then the space-time around it is warped, so that if an object or a light is trying to pass by that massive object, it'll be deflected. So you have a picture of gravitational lensing.
I do have a picture of gravitational lensing. It's funny you should ask.
Yeah.
So here we go. Let me put my screen up. There we go.
Okay. So if you have a galaxy in the distance, and in this picture it's labeled blue galaxy. So
hello, blue galaxy. In the distance,
and then you have a cluster of galaxies in the center. And then us in the Milky Way is over to the side. So the light comes from that distant galaxy, and it is bent around that dark matter because the dark matter kind of pulls the space-time in. So it kind of like warps the space-time around it, so the space-time kind of gets like warped by it and squeezed by it. And so then stuff that's trying to go around it gets deflected. And so the light gets deflected around the dark matter, around all the matter. Mm-hmm. And so we see multiple images of things because, like that blue galaxy is putting out light in all directions.
Right.
But some of the light that was meant to miss us completely. Which is why we're seeing those 3 arrows in this
ray diagram. So and I know for some, I've heard a lot, even with some of my students, that they're confused. Why are there these 3 lines, and what does it show? Yeah. So when we're showing this ray diagram, this is really when we're doing optics and how it goes through a lens. So we're seeing a straight point through the cluster of galaxies, and then what would be on the outer edge of any sort of lens, and if it moves and stuff like that. But it's actually emitting light in every single direction. We're just using this for the diagram. Yeah, so light is going in all directions, but some of the light that should have missed us comes around and bends toward us again. So we see the same galaxy, the same blue galaxy in the background in a few different directions. Because depending on how exactly you line up, you get different numbers of images, but you might see like 3 different images of the same galaxy or 4 different images of the same galaxy. Right. Because some of them like go in different places, and so there are some famous examples of this. If you look up Einstein's cross, that's an example of this, where you have something in the background, and then you have a galaxy, and the galaxy is lensing that thing, and so you have different images of the same thing
because some of the light's been bent around the galaxy or the cluster of galaxies. And
here's
so
one of my favorite examples of showing how it worked and how it's warping what's coming through here.
Yeah. So that's a great image because it shows that warping of space-time. It's weird because that's again a two-dimensional picture of a three-dimensional thing.
Right.
But anyway, so it's warping space-time. So that the amount of warping, the dent, this like depth of that dent is entirely dependent on how much mass you have. So if you have a galaxy or a galaxy cluster, and you can count up the amount of mass in the stars, in the gas, whatever, and then you measure the amount of lensing, there's more lensing than there should be. So you're just weighing that cluster of galaxies, or the galaxy, or whatever is doing the lensing. And what we find when we do that is we find that there's just way more lensing, that dent is a lot deeper than it should be if it was just luminous matter, if it's just regular matter. And so some of that matter, most of that matter, has to be dark. And so the amount of gravitational lensing you see is consistent with like almost all the matter being completely invisible. So that's another way that we know that dark matter is there. So there are lots of different ways that we know dark matter is there. There's that gravitational lensing, there's the rotation curves I mentioned, there's the dynamics of clusters, so the way that galaxies move around in clusters, which is what Fritz Zwicky saw. There's things we see like signatures in the cosmic microwave background that could only be there if some of the matter is this sort of collisionless stuff, if it's this stuff that doesn't interact with electromagnetism. We see like the way that galaxies formed in the early universe. That formation would have been delayed if we didn't have something that was collisionless that could sort of clump together without having the sort of pressure that regular matter does.
So
which is,
we're saying
a complicated topic.
That astronomers and astrophysicists they're not just making it up, going, we don't know, so we're just going to give it a silly name and pretend.
No, so a lot of people seem to think that dark matter is like, oh, you didn't understand it, you filled in a gap with dark matter. How come it's not just that you didn't understand something, that gravity is different or something like that? And we'll talk about that more, I guess, in another episode. But it's basically we just have so many lines of evidence now for dark matter in so many different sort of areas of astrophysics. It would be really hard to explain it away with some other kind of phenomenon. And there are certain attempts to have a different explanation, but most of those work just on a couple of these different like issues, and they don't work for all the big picture. So an analogy I like to use is like you're standing on a street corner, and suddenly you feel a little bit cold, and you see a tree bending over, and you see the street sign kind of wave, and you see some leaves move across a lawn, and you hear a wind chime in the distance, and all of those things happen at once, and you could try to find explanations for each of those things, and maybe a squirrel came up and hit the wind chime, and maybe a cloud passed over the sun and that's why you're cold, or maybe maybe the leaves, I don't know, something happened with the leaves that you don't understand. But
maybe Frosty the Snowman came by you and whispered, that's why you're chilling.
Well, I mean, I don't know. But the consistent explanation that fits all of the evidence is that it's windy, and there's a bit of wind, and you can't see the wind, but you have so many lines of evidence for the fact that the wind just came by that's really the best explanation. That's the simplest explanation. It's the most consistent explanation.
All of those observations. It's not just one. It needs to fit all those phenomena that we're observing. Well, this is something that explains all of these. I could say that it was an invisible unicorn doing something, but it's not fitting, the coldness. We all know that invisible unicorns are really warm, but they might rustle up some leaves now and then. But we need to have something that fits all of those observations, right?
Right.
This is serious business. No laughing.
Right. Yeah. And dark matter is an example of a situation where it's the simplest explanation. Even though you have to hypothesize a new phenomenon, a new kind of thing in the universe. It's called dark matter. It's some kind of new particle. You have to come up with a new particle to explain it, but it's still a lot simpler than saying all of these different things are happening, and an explanation that works with one of them doesn't work very well with the other one. Dark matter explains all of these things pretty well, and there are a couple of little places where we don't understand exactly how it works, or maybe it doesn't seem as consistent. But taken as a whole, all of these things together, dark matter is a really good explanation. So it really is a very sort of evidence-based thing. It's not just like we're making something up because we don't understand.
Right. So we do have a couple other points that we want to hit, but we're running out of time, which is fine because we have more episodes to go, and I did want to answer some questions that are going on. I'm seeing from Twitter and on YouTube here. And it's a question here from Daniel, and he's asking, should we call dark matter faster than light matter instead? So I'm not really understanding the context of that, but I know, Daniel, and I don't know if you asked this before we got into the show, but it's not interacting with light at all, right?
Yeah, and we don't have any reason to believe that it's fast. Like, we know it's some kind of particle, or we're pretty sure it's some kind of particle, but we think that it actually is fairly slow moving. And it doesn't seem to interact with light, but that's not because it's like outrunning it or something. It's just because it doesn't seem to have electromagnetic forces, or it doesn't have that interaction, as far as we know.
So there you go, Daniel. There's another one here from, and I'm sorry, and we already touched on it, but Gabor Kasper, and I'm so sorry if I slaughtered that, but if the existence of dark matter is only based on the behavior of visible matter, how do you know it's a kind of, quote, matter and not another law of physics or fundamental force we don't know about that causes these anomalies? So I think that goes into the metaphor you're talking about, right?
Yeah, so we touched on that a bit. Yeah, so it's basically, it's just when you take everything together, a new kind of matter fits all the evidence really well. It's something that gravitates, something that sort of clusters in a way we think we understand, and you don't have to screw around with the theory of relativity, which seems to work pretty darn well, in order to explain dark matter, if dark matter is a separate thing. If you want to mess with gravity, there are ways to explain some of these phenomena by changing the laws of gravity. But there are certain instances, there are certain examples, and I'll talk about one of them next time. One of them is called the bullet cluster, which you can look up if you're interested, where we see phenomena that really can't be explained just by changing gravity. You really do need an extra component of stuff in the universe. So, it may be true that gravity is not the way we understand it, and it's probably true that there's more to gravity than we know about. It's probably true that Einstein's theory is not, the final answer there, because we know we need to get gravity to work with quantum mechanics, and so far that doesn't work within Einstein's theory. But in terms of what we can see on large scales in the universe, Einstein's theory works fantastically well. And so any change to it is probably going to be pretty minor. And if there is a change to Einstein's theory, that's not going to be enough to take away the evidence for dark matter, because the evidence for dark matter is really strong in a lot of different areas, and you can't do just one little tweak to gravity and fix everything.
Right. Okay. Well, I think it's a good place to end here. So tune in next time, everyone. We're going to get a little bit more into wimps versus machos, how much is really in the universe, and why it's not modified Newtonian dynamics. Why is it not MOND? And our detection methods. So those are some of the topics we're going to be hit next time. If you have any questions for us, or you have anything that you want known about dark matter, let us know. You can leave a comment here on YouTube. But if you're listening to this in the future on iTunes or wherever we're putting this, tweet at us. So, Astro Katie, where are you found?
So I'm on Twitter. That's the easiest way to find me. I'm Astro Katie at Twitter. I am also on Facebook at facebook.com/AstroKatie. I don't update as much on there, but I do put some sort of more detailed explanations of things on there sometimes. I'm also on Google Plus at +KatieMack, and you can find me on my webpage, which is astrokatie.com.
Wow, all the Astro Katie. And you can find me at Scientific Scott. I'm Scott Lewis on Google Plus, and we're over here on Space Fan News. I'm also I have my website of knowthecosmos.com, which is currently being renovated, so it's kind of dusty right now. But we'll get that working a little bit while later. Thank you all for watching, for listening. We definitely appreciate it. I don't know, are we going to be here next week or 2 weeks? I don't know your schedule.
I think we were thinking about 2 weeks from now.
2 weeks from now. All right. So 2 weeks from now, same time, we will see you all over here. And yes, I'm awkwardly ending this show for some reason. So thank you all.
All
I did
right.
see the tweets out there, and sorry we didn't get to all the questions. Thank you, though, for all those, everybody. You guys are great. So we will see you all next time.
Okay, see you. Bye.